Curvilinear coordinate systems 4. Perform this surface integral d sigma dot product with f, where the force F is given by 2 sine theta sine phi e r hat plus 3 cosine theta cosine phi e phi hat plus 4 cosine theta cosine phi e theta hat. And S, the surface, is 1/8 of a spherical shell of radius 2, centered at the origin of the spherical system. The integration region lies in the positive xyz octant of a Cartesian system, as shown below. So this is our r, this is our polar angle theta. So the projection onto the xy plane will give us an angle with respect to the x-axis phi as a azimuthal angle. And we're only performing this in the first octant, positive xyz values on this spherical surface. So the area vector will be in r hat direction. So we need to know the area vector, differential area vector d sigma in spherical coordinate system, and we know that in general the area vector d sigma is given by the scale factors h1, h2, dq1, dq2 in q3 hat direction. So here we have q3 hat is equal to r hat. So this is normal to the surface, and we have to find the scale factors for q1 and q2, which would be theta and phi in this case. So we need to know h theta, h phi, and this will be d theta, d phi in r hat direction. Now we can write a position vector r using our spherical coordinates r sine theta, sine of the polar angle, cosine of the azimuthal angle, cosine phi, r sine theta cosine phi. This is the projection onto the x-axis in ex hat direction. And then we have plus r sine of the polar angle theta, sine phi, which will project us to the y-axis in ey hat direction. And then we have the z component is r cosine theta in ez hat direction. So that's basically the projection onto the z-axis will give us r cosine theta. All right, so we need to know h theta and h phi. Q3 is r, our radial axis. Now we have to look at the derivative of the position vector with respect to theta and take its magnitude. The derivative with respect to theta will give us r cosine theta cosine phi, r cosine theta sine phi, and minus r sine theta. So we're taking the magnitude of this vector r, the derivative with respect to theta, r cosine theta cosine phi in ex hat direction, plus r cosine theta sine phi in ey hat direction, and then we have minus r sine theta in ez hat direction, and we're taking the magnitude of this vector to find h theta. Now this is going to be equal to the square root of, we have cosine theta as the common term here, so this is going to be r square cosine square theta parentheses cosine square phi plus sine square phi, and then the last term is r square sine square theta. and we have to take the square root of this whole thing. Now cosine square phi plus sine square phi, that's equal to 1. So this is equal to square root of r square. Now r square parentheses, I have cosine square plus sine square. So this is sine square theta plus cosine square theta. And we're taking the square root. And that gives us basically r. So our scale factor for the polar axis is r. And now we can do the same thing for the azimuthal axis, phi. The derivative with respect to phi will give us minus sine phi here, plus cosine phi here, and nothing from this z hat part. So we will have the magnitude of this vector, the derivative with respect to phi, minus r sine theta sine phi in ex hat direction, and then we have plus r cosine phi, so plus r sine theta cosine phi in y hat direction. Now we need to find the magnitude of this. So this will give us r square sine square theta parentheses sine square phi plus cosine square phi. So the scale factor is simply the square root of r square sine square theta sine square phi plus cosine square phi and we're taking the square root. Sine square plus cosine square is again equal to 1. So the scale factor is simply equal to r sine theta. Okay, so we can write our area vector, d sigma, the differential area vector, h1, so it's h theta, which is r, h phi, which is r sine theta, so we have r square sine theta, and d theta, dr, d phi in er hat direction on the radial axis. Now that we have found the area vector d sigma and we are given the f vector here written in spherical coordinates, we are ready to write the surface integral d sigma dot f. So we can write this surface integral d sigma dot f. This is the vector f, which is 2 sine theta sine phi in er hat direction, and then it has a component on e phi hat which is 3 cosine theta cosine phi in e phi hat direction, and 4 cosine theta cosine phi in e theta hat direction. And we're taking the dot product with r square sine theta d theta d phi in er hat direction. Okay. Now you can see that the dot product with E phi hat and E theta hat of ER hat is always equal to 0 because these are orthonormal unit vectors. So ER hat dot ER hat is 1. So we're going to have 2 sine theta sine phi here and R square sine theta from the d theta d phi from that part. So this is going to be a double integral to sine theta sine phi, and then we have the area vector r square sine theta d theta d phi. So let's write it this way in order not to confuse things. So first of all, I have a phi integral, and this is going to affect this part. So there's a sine phi d phi, sine phi d phi, and then I have a theta integral, which will affect this part, 2 sine square theta, and there's also r square, but r is equal to 2. So I can just evaluate that r is equal to 2. So I will obtain 2 square, which is 4 times 2. That's going to be 8. So we will have an 8 up front. Then we have sine square theta d theta that we need to evaluate. Now I have to think about the limits of this integration. Positive xyz octant, that's what we're talking about, positive xyz values, 1 octant. This implies that theta is going to be in between 0 and pi over 2, and phi is also going to be in between 0 and pi over 2. So theta equals 0 is here, theta equals pi over 2 is here, so that's basically defining this slice, and now we're going to rotate that slice by varying phi from 0 to pi over 2. So that's basically our projection onto the xyz plane. Here, this is our projection onto the xyz plane, and that defines the angle phi. Okay, so with that in mind, I can now write my limits of the integration. So I have 8. Now the integral sine phi d phi is minus cosine phi, minus cosine phi. This will be evaluated between phi equals 0 and phi equals pi over 2. Then I have sine square theta d theta. Now I can recall that cosine 2 theta is 1 minus 2 sine square theta. So for sine square theta, I can substitute 1 minus cosine 2 theta divided by 2. So for this second integral, 0 to pi over 2, I have 1 minus cosine 2 theta over 2 d theta. Okay, so the phi integral will give me minus cosine pi over 2, which is 0, minus minus plus cosine 0, which is 1. So I will have 8 times 0 plus 1. And for the theta integral, the integral of d theta over 2 is theta over 2. So I will have theta, simply theta over 2. And for minus cosine 2 theta over 2, the integral is minus 1 over 4 sine 2 theta when I take the derivative, this 2 will come up front, make it minus 1 over 2, and sine will turn into cosine. And this will be evaluated between theta equals 0 and theta equals pi over 2. So let's do that. So this will give me 8 times. When I substitute theta equals pi over 2, I will obtain pi over 4 for theta over 2, and for 0 I will obtain 0. And then I have minus 1 over 4. Now sine 0 is 0, but sine 2 theta is going to be sine pi minus 0, so plus 0 will be this part, and sine pi is also 0, so this is going to give me no contribution, and therefore my answer is going to be 8 pi over 4, which is 2 pi. So I can finally write my answer for the surface integral d sigma dot product with my vector f for the first octant is 2 pi. This is our final answer. Okay, so in this problem we performed a surface integral d sigma dot f. Force f is given in spherical coordinate system, and the surface is first octant of the sphere. That means x, y, z are positive. Theta varies between 0 and pi over 2, and phi varies between 0 and pi over 2. And our area vector must be perpendicular to the surface in r hat direction. So that's what I did here. So in order to find the differential area vector, d sigma, I have to know h1 dq1, h2 dq2 in q3 hat direction. The scale factors are found by writing the position vector using the coordinate transformation between r theta phi and x y z. So this is x ex hat plus y ey hat plus z ez hat. When I take the derivative with respect to theta and take its magnitude, it's equal to r. Derivative with respect to phi, take its magnitude, it's equal to r sine theta. So r sine theta, r square sine theta, d theta d phi, er hat is my area vector. So when I take the dot product of this with the given vector, it's only going to have a non-zero value for er hat dot er hat. Er hat dot e phi hat is 0, er hat dot e theta hat is 0. So this will give me 2 sine theta sine phi, r square sine theta d phi, and r is equal to 2. So that's given. So this is going to be 4 times 2, 8. Integral over phi, sine phi d phi, integral over theta, sine square theta d theta. And the limits were determined to be 0 and pi over 2. So sine phi integral, sine phi d phi gives me minus cosine phi. To evaluate sine square theta integral, I use this trigonometric identity. Cosine 2 theta is equal to 1 minus 2 sine square theta. And when I evaluate these two integrals between 0 and pi over 2, I obtain the final answer to be 2 pi.